started. Do you have your targets written down? Need some paper?
I think I need a paper. Yeah.
Good thing you're in the front row.
Yeah.
You know all your errors.
It's probably facing the right way, right?
Yes, it wasn't me.
Yeah. I can catch it.
I don't want to hurt you.
Okay.
I can't throw. Okay, there is this, finally, at last, you learn about this thing called the fundamental theorem of algebra.
Finally.
It has a big name. There's a lot of things to be discovered in algebra, but this is the fundamental theorem. It says, fundamentally, now that you're in algebra 2, it's time to talk about the fundamental rule of algebra 1. Every polynomial equation with a degree greater than 0 has at least one root in the set of complex numbers. Okay, doesn't that make sense to you? Basically, every polynomial equation, whether it's cubic or quadratic or quintic or 7th degree or 8th degree, has a root. Not just in like where it crosses the x-axis in our coordinate plane with real numbers, but it has a root in the set of complex numbers, which includes imaginary terms. Okay. Cool. So even if you have something quadratic, like y equals x squared plus 2, which would be up to, it doesn't have any zeros in the real plane. It has 2 zeros in the complex plane. You with us, Brendan? Barely. So for example 1, we can actually, we're going to solve these, and then we're going to state the number and the type of the roots that we see. A lot of this is stuff you know how to do already. Okay. For a, x plus 3 equals 0, how do you get the x alone? Subtract the 3, and so x becomes... Now, our question is, what kind of a 0, what kind of a root does that equation have? Well, it's one solution. Is it real or complex? Real. One real solution. So if you were to graph the equation y equals x plus 3, you would find that the 0 is located at negative 3. Okay, how about b here? X squared minus 8x plus 16. How do we solve that? Factor rules. Okay. Since it is, what does it factor to? X minus 4 times x minus 4. So how many solutions does this thing have? This is one of those where it crosses in one place, but we call it a double root. So it has 2 solutions in the real plane. 2 solutions in the real plane. Real. But we call this a double root. So here's the trick. Yes, sir. Why is the what? Here? Well, if you multiply this out, this becomes x squared, right? And then x times negative 4 is negative 4x. Here's another negative 4x, negative 4x, and negative 4x make the negative 8x. So this one's always the sum. That one's always the product. So if you add these together, you get negative 8. If you multiply those together, you get 16. So these 2 solutions are real. This is called a double root. And this will tell you, I'm going to give you the hint now, and I want you to remember it forever because it's really important. If you have 1, 0 at 4, or at any value, you need to use synthetic substitution and try it again, because sometimes you have double roots. The only way to do that is to try it. So when you get some kind of a polynomial that may be cubic or quartic or something, and you know that there's a 0 at 4, don't just try it once. Try it twice. at least twice. Try it 3 times. If it works twice, keep trying it until it doesn't work anymore, and then try to find another 0. Because it's kind of a complex guessing game with some little cheats on how to get all the zeros. And one of those little cheats is to always look for double roots because they creep up on you. If you don't do that, if you don't know that there's a double root here at 4, you'll find one at 4, and then you'll spend eternity looking for another one. And then you'll get so frustrated you're going to get mad and give up. So try the double root thing. It works.
So how do we write that?
How do you write that?
Like the end root, like x is equal to
4, comma 4. Or you could just write x equals 4 and then next to it write double root. But I'll see it in your work because you're going to do the synthetic division thing, synthetic substitution thing to find the zeros, and I'll see it in your work. But when you list them, you can list them as x equals 4 and whatever else the other zeros are. This one only has 2 because it's subtract. Okay, let's go to C. How about x to the 4th minus 1? Is that factorable? It is. How does one factor it? Difference of squares. So I have an x squared minus 1 and an x squared plus 1. Now I have another difference of squares lurking within x squared minus 1, right? So this would be x plus 1, x minus 1, and then x squared plus 1. How many solutions should I expect? 4, so don't give me 2. Here are 2 of them. X equals negative 1, x equals 1. What's the solution to that? X squared plus 1 equals 0. Well, say we'll use the zero product property and find out. I know that x squared plus 1 equals 0. How do I solve for x? Subtract the 1. What do you do now? Take the root, right? Don't forget when, yeah, you're going to get I, but it's got to be plus or minus I, because there are how many answers here? 2. Don't forget the plus or minus. X equals plus or minus I. And that gives me 1, 2, 3, 4 answers. Yay! I did a good job. So you can tell by the degree whether or not you've got them all. 1, 2, 3, 4. Oh, that looks confusing. Let's go like that. So there are 4 of them. And how many of these are which type? Well, these 2, the negative 1 and the 1, they're real. And how about I and negative I? Those are 2 complex roots. Or imaginary roots. Okay, key concept number 2, which I've already told you like a whole bunch of times. This is the corollary to the fundamental theorem of algebra. A polynomial equation of the form p of x equals 0 of degree n with complex coefficients has exactly n roots. What that's really saying is this. A polynomial function of nth degree has exactly n zeros. So if it's degree 4, how many zeros does it have? 4. If it's degree 12, how many zeros does it have? If it's degree 3, how many zeros does it have? If it's degree 4, how many real zeros does it have? Who knows? It might be 0, it might be 4, it might be 2. What about 1 and 3? Oh, that leads me to the next thing. So here's Descartes. He came up with this thing called the rule of signs. It's pretty cool. And I think sometimes these things, like when you try to read them with letters in it, it's more confusing than when you actually do a problem. That helps you understand what it means. But you can find out how many possible real zeros are positive and how many possible real zeros are negative using this little rule. Really cool. It's called the rule of signs. So you take y equals p of x, which is the function, and then you look at all the signs between the coefficients of the terms. And you do the same thing for p of negative x. So I'll show you what this looks like, and then I think it'll make more sense to you. But remember I told you that looking for the zeros is like a guessing game? These are some of the shortcuts to playing the game well. Here's a function p of x. What degree is it? It's fifth degree, and what do we call that? Quintic. This is a quintic polynomial, and it has how many zeros? 5. So you know you need to add up to 5 zeros. So let's look at the sign changes. If I take p of x, which is the polynomial in its original form, and I copy it down, why don't you count to see how many sign changes there are between each term while I write it down. You know what a sign change is? You know what I mean by that? If you look at the first coefficient, what's the first coefficient? What is it? Hunter's the only one who knows. The leading coefficient is positive 1. Is there a change in sign between the coefficient of the leading term and the next term, negative 6? Yes, there is a change in sign. Change. How about between negative 6x to the fourth and negative 3x cubed? No, not there. How about between negative 3x cubed and 7x squared? Yes, there's a sign change there. How about between the quadratic and the linear term? There is. How about the linear and the constant term? There is. How many are there, sign changes, that is? 4. So we're testing right now the positive sign changes, because this is p of positive x. How many possible sign changes are there that are positive? So the possible positives are 1, 2, 3, 4, and then it goes down by 2's. So 4 or 2 or 0. So there are either 4 sign changes, or 4 possible zeros that are positive, 2 of them, or 0 of them. It's kind of good to know, because if you come up with all 4, you know you've done it. But if you come up with 2, then you know there's 2 more. Okay, now how about the negative ones? Well, for the negative ones, instead of taking p of x, you're going to take p of negative x. So what does that mean when you take p of negative x? Well, there's a negative x that goes in the place of every x, right? So this looks like negative x to the fifth minus 6 negative x to the fourth minus 3 negative x cubed plus 7 negative x squared minus 8 negative x plus 1. This looks hard, but I'm going to show you that it's not. The only place where the sign actually changes is when the degree is what? Well, let's try this out. Negative x to the fifth, is that going to give me a positive or a negative x for an answer? If it's a fifth degree, I'm going to have negative x times negative x, that's positive, times negative x, that's negative, times negative x, that's positive, because negative times negative is positive, and then times negative x again, which makes it negative. So an odd degree is going to change the sign from positive to negative. How about the even degree? Because I'm finding p of negative x, so I can find the negative possible zeros. So if it's negative x to the fourth, it's going to become positive, which keeps it at negative 6x to the fourth. See how the even degree didn't change when I entered the negative in? So now this one's odd, so what's that going to do to the sign? It's going to change it to positive. And how about this odd or even degree, the squared? Well, that's going to keep it the same. And then the odd degree here is going to change, plus 8x plus 1. Now we're going to do the exact same thing that we just did with the possible positives. We're going to find the possible negatives. let's count them. How many sign changes are there? There's just one between the quartic and the cubic term. One. So then how many possible negatives are there? Just one. Is there another option? No, there's only one. The great thing about it is when you have an odd number of sign changes, you know that there's one that exists. See, when it's even like this and you get 4, 2, or 0, there could be 4 of them or there could be none of them. And you could be poking in the dark all night long and you can't find one. But if it's odd, the world rejoices because there is one out there. So if you were looking for the zeros of this function, you would start by looking for negative zeros. Yes,
So
Dustin?
when there's a negative one, you can have any even if you're saying that function.
Yes. Until you get to 0, and you can't go into negative territory. That's why -1 is not on the list for the bottom one. Okay, so then you can state the possible ones. There's either 4 positives and 1 negative, and that's actually about it. So you can make a table out of all of this as well. I think I have one lurking here.
Whoa.
A long time. So here's a really cool table you could come up with. Hunter already told us that we know that there's 1 negative real 0 all the time. Now, we could come up with, if there's 1 negative real 0, we need to have 4 positive real zeros, right? But then there are also imaginary zeros, the ones that we can't really test with Descartes' law signs. So if there's one negative, then there have to be 4 positives, and that would leave us with how many imaginaries? 0. But if we have 1 negative, we could find only two positive real zeros, and then we'd have to have 2 imaginary zeros. See all the possibilities here? The 3 possible combinations. You want to either make a table like this by hand, or you want to think about this table in your brain, and while you're testing for these zeros and probing around. One of these problems may feel like they're long, but there aren't many. I'm not going to give you more than 2 of these tonight to do. And I will show you more and more hints as we go, because I just don't want you to die working on a problem forever. Because you're not used to it. You haven't trained your brain for that yet. Any questions about the table? Heidi? Do you have to make the table? No, but you need to understand that if you find a negative 0, then you have the option of either having 4, 2, or 0 positives. And if you have no positives and only 1 negative, then the other 4 must be imaginary. So this will help you because if you find 1 negative and 2 positives, you can use synthetic division, synthetic substitution, to come up with the depressed polynomial, and it'll become what? If this is 5th degree to start with, when you pull this one out, it becomes 4th degree. When you pull these 2 out, it becomes 2nd degree, right? And when it's quadratic, you can find the imaginary zeros using the quadratic formula. Okay.
That looks like 7. Is that
I will not give you the 7th degree polynomial, but it
still work?
yes, it still works.
How
It's
many
just
imaginary
it just depends on how the law of signs works, and then you can figure out how many. But one of the things we're going to learn is that imaginary zeros always come in sets of 2. So if there's a positive imaginary one, there will be a negative one that goes with it. They come in pairs. So if you have 7th degree, maximum you could have is 6 complex zeros, and one of them would have to be real, be a positive.
Would there be negative imaginary zeros?
No.
Okay.
Because that doesn't exist. You can't have a negative amount of imaginary zeros.
That's why I asked the question.
Okay.
Tripping me out.
Nope. Hunter.
What if negative 0 not negative 0
Then you would have 3 or 1. But you know that 1 exists, so start there. The odd ones are a good sign. The even ones, no. Okay. Yeah, you're going to do 1. Are you going to do 2? Oh, there's more stuff. I want to do this first before we do that. This is really quick. I was just telling Casey about this. This is called the complex conjugates theorem, and it says if you have an imaginary or a complex zero, you have two, because they come in pairs. So you cannot have an odd number of them. This is good to know. Gets that? So if you have imaginary zeros, they come in pairs of two. So you can't have just one. You have to have two. So there's a positive one for each positive one, there's a negative one, because they come in pairs. So that's really good to know. So if a plus bi is a zero, then a minus bi is a zero. Good to know. Okay, example 3. We're going to find all the zeros of this function. Yay! So let's start with we're going to look at f of x, and we're going to look at f of negative x. Right? We'll look at f of x to find the positive real zeros, then we'll look at f of negative x to find the negative real zeros. So for the first one, if I'm just looking at f of x to find the positive ones, how many sign changes exist that are positive? If you need to draw the arrows, draw the arrows. 1, 2, 3. I'm already happy, because I know how many positive ones are there. Possible positive zeros. That will be 3 or 1. Now if I make it negative, f of negative x, remember the only thing that changes when you have f of negative x are the odd degree terms. So will x cubed change? Yes, because it's odd degree, so it's going to become negative x cubed. Will negative 4x squared change? No, because it's even. And then 6x will change in sign because it's odd degree. And then I still have minus 4. How many sign changes are there? None! Now I'm super happy. Oh, oops. Wow. Possible negatives. There are 0. So if I made this little table in my brain and thought about this, this is a cubic polynomial, so how many zeros does it have? 3. What's the possibilities? I can have either 3 positive, real zeros, or I can have 1 positive real zero and what? 2 imaginary zeros. Yay. So that means if I find 1 zero only, then I can find the depressed polynomial and find the rest of the zeros using the quadratic formula or factor, or completing the square, or bracket, or whatever else. So my suggestion is find the one that's odd. Here we have positive. We're going to look for positive zeros that are real. We're going to use synthetic division, and we're going to try numbers that are whole. Random right now. On Monday I'll show you how not to be random, but be selective. What's that? I like to start with 1. So, I just like to be easy. I'm not picking a number like 58 to do synthetic division with right now. No, thank you. Okay, so let's start the synthetic division thing. I'll show you how to do this really quick. The synthetic division actually happens in your head. I'll show you that. Thank you. So you write them down. 1, negative 4, 6, negative 4. You can make a little table out of it if you want. People do that. Get kind of into it. Okay, I don't really get that into it, but 1, 2, 3, 4. Wee, wee, wee. Should I show you one that looks like one of those? Good. Yay. Okay. Let's start with 1. If there's a 1, what do you do with the 1 that's up here? Okay, you might need this on the side just for the first one. So 1, negative 4, 6, negative 4. The 1 would go in the box. And then what would I normally do? I would bring this one down, and then I would do what? Multiply them together, and then add these, right? What we're going to do is we're basically going to skip everything that's in this line. So I'm going to start with 1. I'm going to multiply 1 by 1. That's 1. Add it together to negative 4. What is that? Negative 3. So that's what would happen here, negative 3. What do I do with the negative 3? Multiply by the 1. That's negative 3. Add it to the 6. What's 6 minus 3? So that would go here, right? And then 3 times 1 is 3. Add it to the negative 4. What do you get? Did we get 0? So you're done with 1 then. Try 2. So now we're on to 2. So you bring the 1 down. Still 1. Multiply 1 by 2. 2. Add it to negative 4. Negative 2. Negative 2 times 2. Negative 4. Add it to 6. 2. 2 times 2 is 4. Add it to negative 4.
Whoa.
0! Yay! There's this whole moment of jubilee when that happens. And you don't get it yet, but it's really rewarding. So now what? Well, now I know that 2 is a 0. So that means that, what? What's my depressed polynomial that comes out of that? So first off, I know 2 is a 0, so got x minus 2. And then what's left inside? What's the depressed polynomial? Negative 2 x squared plus 2x. Oh, sorry, I was wrong. 1x squared, right, because this is our x squared, minus 2x plus 2 equals 0. How do you solve that? Well, you try factoring. Does it factor? No, it does not. So what will I have to do? Use my quadratic formula. And when you do that, you'll find that 2 of these answers are complex. But you're done. You found all the zeros. You can find the zeros, and then you have all 3. Questions? For the 2 problems that I have assigned for you tonight, I want to see all your work. Quick. I will not give you one that is like that. That will not be. And you want to try numbers that are small because I'm nice. Okay, keep that in mind. Whoa, you don't think you're done, but you're not done yet. There's one more thing. I know, school's hard. Just wait till you're done with school, then it gets harder. So, we can also write a polynomial function with integral coefficients if my zeros are 3 and 2 minus I. So now I give you the zeros and you write the function that goes with it. So if 3 is a 0, what is a factor? X minus 3. Okay, now here's where it gets tricky. If 2 minus I is a factor, then I could say, okay, this is x minus 2 minus I. What else is a factor? Remember, what did I tell you about these complex roots? They come in pairs. So if 2 minus I is a factor, what else is a factor? Negative 2 plus I. So this would be x minus negative 2 plus I. Now you would have to multiply all of this together, and what you're going to find out when you do this multiplication piece is that these i's disappear because it becomes I squared. And what is I squared? Negative 1. So when you multiply all this up, which I know we don't really have time for, but you're going to find that the i's disappear. Tomorrow, please remind me to do one of these with you, because it gets complex, and I know there's one on the final. Well, then on Monday.